I'm Ryan Barr. I'll be talking with you about energy and climate change mitigation today. And then we're going to zoom in on one especially exciting opportunity, which is to reuse electric vehicle batteries to store electricity and thus integrate more renewable energy. Need this. So, how do you mention this report? Start with a quote from one of the authors. He said that the report shows that we have only the slimmest of opportunities remaining to avoid unthinkable damage to the climate system that supports life as we know it. It's pretty sobering. Basically, we're running out of time to limit warming below 1.5 degrees C. And to do that, renewables need to dominate the global energy mix. We need to reach a majority of electricity generated by renewable sources by 2030, and almost all of it by 2050. So quick show of hands, who thinks we will accomplish this globally? How about in the US? Okay, I think we need to dream a little bit bigger. Our options here are hydro, wind, solar, biomass, and geothermal. And naturally, since I'm coming to you from California, I'll be talking mostly about solar today. We're at about 17% nationally right now. 33% or so in California. And this question, how do we get from 33% to 50 to 75%? This really motivated me to quit my pointless management consulting job and move across the country to be a poor grad student. So I'll set the stage by stating the obvious, which is that it takes a suite of solutions to accomplish our renewable energy goals and our decarbonization goals. We do need a lot more renewable generation, but we also need to probably expand our transmission networks and increase collaboration between grid operators. So this is a plea to the future policymakers of Washington to share your hydropower with California. We also need to make demand more flexible so that we're using energy when renewables are abundant. We need to store energy at scale, unlike we ever have before. We need to extend the benefits of grid decarbonization to the transportation sector by electrifying light-duty vehicles and buses, for example. And we need to charge those vehicles at the right time, and I encourage you to ask me about that later. We also need to modernize our building stock, make them more efficient. And this is what I mean by electrification. We need to electrify buildings and electrify transportation. So we have this suite of solutions, but I'm really going to be focusing in on one solution that's sort of at the nexus of these three sectors, which is reusing electric vehicle batteries to store energy, to integrate renewables. So California utilities have built a lot of big solar farms. Solar PV on the top here has dominated procurement since 2012, and this trend is likely to continue given that we have this 100% clean energy goal, whatever that means. We have a 50% renewable portfolio standard that is law by 2025, and we'll hit that. But what this 100% clean energy goal means to me is we need to stop burning gas to balance the electricity grid, and we'll talk more about that challenge. So that was utility scale solar. This is rooftop solar, which has also exploded in California, thanks to rebates beginning around this period here, and also to a policy called net energy metering, which basically allows people with rooftop PV to export their excess solar to the grid, and it compensates them very generously for those exports. This policy will go away, as it has in Hawaii already, and what that will incentivize is for people to store their excess solar instead and use it at a later time. So this trend will also likely continue despite that change in net energy metering, because we also have this requirement for new homes to have rooftop solar, which is unprecedented and pretty amazing. With millions of homes being powered, at home with panels on the roofs, which is inspiring to me. So those are success stories, but now we have a solar problem. We have too much. So this is renewable generation, wind and solar exclusively, in the California ISO. So here on the bottom is wind. Here is our utility solar. Here's our rooftop solar. But here, what I want to point out is what we had to curtail on this day in March of 2017. So this is 6 gigawatt hours of energy that we just threw away. We wasted because we couldn't integrate it into the electricity grid, and that could have powered almost 500,000 homes during that time period. So I view this as an opportunity, and what that overgeneration is causing is this phenomenon. So another quick poll, who's familiar with this figure? Okay. It's called the duck curve. And I worked for the California ISO this past summer, and I can tell you that this does in fact haunt the dreams of grid operators right here. So the challenge is that this is a figure of net load, which means electricity demand minus solar production. And it's for a typical spring day, and spring is important because that's when we have lots of solar and little demand. So what this is showing here is year after year, as we install more and more solar, we move down this curve and we get a deeper belly and a steeper ramp here. And during this belly of solar overgeneration, we have curtailment, which we talked about, but we also have negative wholesale prices, which is also amazing. We're paying people to use energy instead of charging them because we have so much at this time. So I also encourage you to ask me more about that. And then during this ramp, the grid is very strained, and this is when operators are firing up gas generators to balance the grid. So this is when we have a lot of emissions and really high prices for electricity. And this is driving the need for energy storage. So it's very likely that we will replace the gas generators that we're using here with really big batteries to charge during this period and discharge during this period to sort of flatten out this net load curve. So let's talk about the effect that has on everyone's favorite topic, which is electric utility rates. The bottom line is that electricity used to be most expensive in this period between 12 and 6, and that's changing. It's now most expensive during 4 to 9, during that ramp period that we talked about. And so another way of phrasing this is that generating your own electricity used to be the most valuable during 12 to 6 when the sun was out. And now it's most valuable between 4 and 9. So it's out of sync with the solar production. So this motivated me to do a bunch of case studies on the economics of rooftop solar and storage and how that's changing with these new rates. And I'm going to talk about one. So this is a typical supermarket near Los Angeles. Under the old rate structure, they could save about $90,000 a year by installing a solar system on the roof, which was a sweet deal. They couldn't save much from storage. And when we shift to these new rate structures, and that shift is already underway, the savings from solar is cut in about half, and the savings from storage is pretty much doubled. And the bottom line is that these ongoing shifts in electricity rate structures, including this peak price period, and also the net energy metering change we talked about, is going to devalue solar production and encourage energy storage. And this is already happening. So this is one of many factors that is driving these explosive growth projections for storage. And I wouldn't pay too much attention to this breakdown of utility, commercial and industrial, and residential because no one has any idea. But one other thing driving it is California's energy storage mandate. One thing I've learned about California politics is they love to pick a technology and mandate it. So this is going to add about 1.3 gigawatts by 2020, which you can see is a very significant portion of this projection. Another thing driving it is that we just extended this program, which will provide another $800 million in rebates for these small-scale battery systems installed in people's homes and at their businesses. So this is going to add another 3 gigawatts of storage before 2026. And so this is explosive growth, right? But it pales in comparison to battery production for electric vehicles. This is Bloomberg New Energy Finance, their projection. It's consistent with others. We see that electric vehicle batteries account for 20 times as much storage as we'll need for these stationary applications. And we need to manage that waste stream effectively. An encouraging point, though, is that about 70% or more of the capacity of these electric vehicle batteries is maintained after their useful lives in vehicles. So this is an awesome opportunity for us to reuse the electric vehicle batteries. So this has all motivated our work at the Green Technology Laboratory, where we are reusing electric vehicle batteries to enable this renewable energy transition. And so we test the health of batteries when they come in, and we test how they degrade over time as we continue to charge and discharge them. We remanufacture these second life packs. This one is 2 kilowatt hours, so you can hold it in your arms and it weighs about 50 or 60 pounds. We also develop battery management systems. This is the hardware that goes on each module and measures its temperature and voltage and current, keeps it safe. And then we also develop energy control systems, which tells these big batteries when to charge and discharge. Charge when we have solar during the day, discharge in the evening to reduce our peak demand. And where we are today is we've developed this working prototype in our lab. This is 150 kilowatt hours, so it's about 75 times that small system I told you about. And in the next month or two, we're going to drop this system at the Robert Mondavi Institute at UC Davis, operate it there to reduce their peak demand and demonstrate that it works in the field. And then I'm representing this lab in a couple of new venture competitions that are coming up, the Big Bang competition and Big Ideas competitions in Davis. And the goal there is to raise money to develop our first product to bring to market. And because I think, honestly, the quickest way to mitigate climate change is to do it profitably. So we're going to use this system to reduce people's electricity bills and increase the value of their solar systems. And just to wrap up and kind of restate my thesis in 3 parts, renewables are required to decarbonize our global energy systems, and we can do it affordably because of how cheap wind and solar are, for example. But the intermittency of renewables is driving the need for energy storage. In California, that sort of manifests itself in the form of this duck curve, but where there's lots of wind, that leads to very volatile electricity prices that energy storage can also help to mitigate. And electric vehicle batteries will be upcycled to meet this grid need for energy storage. Thank you.
So how many electric vehicle batteries are actually out there to be recycled, and what's the capacity you can actually generate with them?
So, we have about 500,000 electric vehicles in California at the moment. That's about half of all the electric vehicles in the United States. But we're predicted to, one headline I should also include here is that California has a 5 million electric vehicle target by 2030. So we're going to 10x the number of vehicles, electric vehicles that we have in California by 2030. And so the bottom line is that we'll have more than we need, more than we know what to do with, actually. Yes?
So all these batteries also need resources to produce them. Do you have a sense for how much of a limit does resource availability place on battery production?
Yeah, so there are scarce metals involved in producing these batteries, cobalt. We also use nickel, manganese, but there's plenty of metal out there, and miners are scaling up production to meet this impending battery demand. And innovation is constantly happening to use less and less of the metals that are scarce and expensive. So it's not a showstopper. Yep.
Yeah, my question is kind of related to that. I know that there's been concern over the environmental impacts of producing all these photovoltaic cells and batteries. And I was just wondering if that's a concern that you thought about any, and if that's still a problem, scaling up solar and battery storage likely to affect that.
Yeah, so the life cycle analyses on solar and storage are interesting and worth looking at. And there are environmental impacts of producing both, but they're still really beneficial from a climate perspective.
We have time for one more question.
So the graph a few slides ahead of this, you didn't have a time scale on it. What are you seeing in terms of how long,
Mhm.
the scatter plaque, the blue with the, anyway, how long are you planning on, how long are these batteries continuing to last and what's their capacity? Because they're achieving 70% when you get them and try to upcycle them, but what's your expected lifetime for that upcycled battery? And how does the battery capacity decrease over time?
Mhm. So our results are showing that when we test these batteries, pick the healthy ones, remanufacture it, it can last for about 7 years, and over 2,000 cycles, only 20% of the further capacity is lost. So
So over 2,000 cycles over 7 years?
yeah,
Okay.
those are our preliminary results, but that is a better question for the battery engineers in our lab.
Okay. Thank you.
All right, let's give Ryan another round of applause.